In this next series of videos, we're going to look at an important application area for calculus, which is the area of related rates. The fundamental idea, suggested by the name, is that we're going to use rates of change, say something like a velocity, and use that to calculate the rate of change of another function or another variable. And so we're relating the two rates. The key connection here is that the rates we're talking about are the derivatives that we've seen earlier. Related rates problems are typically word problems. The best way to get good at these is to practice them, so we're going to work through a series of examples and show how the skills that we learned earlier with implicit differentiation apply to these scenarios. Let's take a look at the example in front of us here. We have a car that starts driving north, so the car is starting here and it's going to move north on the map. It starts at a point 150 meters east of an observer. So we have an observer at this point here, and they start 150 meters apart. The car is going to be traveling north at a constant speed of 20 meters per second. So that's our rate, number one. And we're asked how fast is the distance between the observer and the car. So the observer to the car here, or the observer to the car as the car moves north. And we're asked for how fast, which is going to be another rate. So our goal here is to associate or relate the rate that the car is moving north with the rate at which the distance to the observer is changing. What I find most helpful for these kinds of problems is to draw not just one diagram, but preferably a sequence of diagrams which indicate what's happening over time. All of these points, all of these values are changing with time. So if we imagine what this picture would look like at, say, time 0, where the car starts here and is moving north, and after 1 second where it's 20 meters north, after 2 seconds it'll be 2 times 20 or 40 meters north of there. And what we're capturing is the distance from the observer to the car. What is fundamental in these problems, but can be a bit counterintuitive, is this important lesson. When we want related rates, we don't actually start there. We start with relationships or quantities, and this is the emphasis on start with, not the rates. The rates will come later. We will get to them, but they come with calculus after we've studied the general case of just how variables are related. So the first thing we want to do here is define not how fast is the distance between the observer and the car changing, but what is that distance? So let's call that x, a variable name that's convenient. So x is going to equal the distance from the observer to the car. Then we can look for common patterns. Well, in all these different expressions here we have x. We also have the base of this triangle is consistently 150 meters. That was given in the question. And last but not least, we have the distance vertically here, and that's changing. So we want to give it a variable name. So notice we give some things variables, x and y, and some variables, well, some things are not changing, so we give them constant values, like the 150. Let's define the y more explicitly here. Y is going to equal the distance north of the start point. What we can do then is look at all these diagrams and see what they have in common. With the boundary case being this, but these two here being more representative, we can see that every time we look at this diagram, we have a right angle triangle where the 150 and y make up 2 of the sides and the x makes up the hypotenuse. So we can make this statement, which is always true, which is that 150 squared plus y squared is going to equal x squared. Note that this is a property about the quantities x, y, and 150. How do we get to the rates? Well, let's take a look at how we've defined these two things here. The constant speed of the car is how fast this y length is changing. That rate is how y is changing with time. Meters per second gives us the clue from the units. We also have how fast is the distance to the observer changing. Well, that's the distance to the observer is x, and we're asking how quickly is it changing with time. That is another time derivative. So here we have that related rates idea. We have the rate dy dt. We want the rate dx dt. We want to relate those two rates with some mathematics. All right, let's see how we can do that with the application, very careful application of implicit differentiation. We're going to found our approach on this equation here on the next page. We have 150 squared plus y squared is equal to x squared, no matter where we were in that sequence. And we can actually put in a little recognition that x and y both change over time. They're functions of time, so we could put bracket t beside them if we felt like it. There are also two quantities. Everything on the left-hand side here is equal to the quantity on the right-hand side. So what we can do, if those two sides are equal, is transform both sides in the same way, here by taking the time derivative, and see what happens. So we'll write that out explicitly here. We're going to take the time derivative of 150 squared plus y squared. That's going to equal the time derivative of the x squared. And it's so important that you keep track of what variables mean what in these problems. Notice x and time are different variables, just like y and time are different variables. The ideas will be exactly the same as what we saw with implicit derivatives though. Let's walk through this equation and ask, how does 150 squared change with respect to time? Well, we're going to get a 0 for that, because the derivative of any constant with any variable is going to be 0. Well, what about the y squared? Well, the y squared, any derivative of y squared is going to be 2y to the power 1 times the derivative of the inside. And here you just got to be careful with what derivatives we have. Y is our variable, and t is the derivative we're taking. So we get dy dt, and we're done. On the right-hand side, we get the same idea. We have x squared. The derivative of x squared is 2x to the power 1 times the derivative of the inside, the derivative of x, with the respect to the time variable that we're using in our derivative. So notice that we get two time derivatives out of this because we took the time derivative of both sides. There's a real temptation to overthink these calculations, especially the derivative step. Literally, we're doing exactly what we did with implicit differentiation, and we're literally applying the rules of differentiation. What's the derivative of some function squared? What's 2 times that function to the 1 times the derivative of the inside? And all we're doing is being very clear about what the variable inside was and what the variable of the derivative was. If you do that carefully and cleanly, we're not doing anything new, and the answers that we're looking for just pop out. Let's see how that works right now. We want dx dt, and we notice that we actually have related our rates now. If you take a look at our equation, we have the speed of the car going north is somehow related to the quantity that we care about, which is the distance between the car and the observer. And so we're just going to solve for this a little more explicitly. And we'll have dx dt is equal to everything on this side, 2y dy dt, and then divided by 2x. So again, nothing out of the ordinary here. We're just manipulating the symbols. And we can simplify that a little bit to y over x dy dt. And that gives us the rate of change of the distance to the observer, derivative of x with respect to time, and x was the distance to the observer from the car, and dy dt was the speed of the car. And that we actually knew, which was 20 meters per second. All right, we're almost there. In fact, we're looking for this value here. We have dy dt. We just have to go back to the question to fill in some other ingredients here. Let's go back a page. We're asked how fast is the distance between the observer car changing after 10 seconds. So that's the last missing ingredient. And here, it depends on the problem, but what we can say fairly conclusively, because the situation for the car is fairly simple, is that after 10 seconds, we need to know the y and the x quantity. Well, what we know is So there's our x, our y, and our 150. After 10 seconds of moving at 20 meters per second, we know that y is going to be 20 meters per second times the 10 seconds, which is 200. That gives us the y in our formula. We do need to solve for x, but that's not too bad either, because we have our relationship at the top that x squared is equal to y squared plus 150. And so we get x squared is 200 squared plus 150 squared. Let's label that. Let's call that 1. And that leads to, with a bit of calculator work, exactly 250 meters. Goes with a 3, 4, 5 triangle if you're wondering why we got such a nice round number. And that's perfect. We have dx dt is this ratio here times the speed of the car, and we have x and we have y. So we'll just add this in the bottom here. At t equals 10 seconds, dx dt is going to equal y over x, 200 over 250, times dy dt, which is 20 meters per second. That's 4/5 of 20, which will be 16 meters per second. And that is our first related rates problem. Just going over the fundamental steps, there really are two anchor points. One is to come up with the relationship between the quantities in the problem, here the distances, and we come up with some equation there based on our knowledge of geometry. And then the second major step was to take the derivative with respect to time of both sides and carefully apply the rules of implicit differentiation. You'll see that theme throughout our related rate section.